Okay, now we will cover the speed and torque characteristic. Okay, so normally the torque and rotational speed actually is inversely proportional to each other. Okay, for example, the higher the torque, the lesser the speed. Okay, so when you have a higher speed, means that the torque is very low. Okay, so therefore the lines is, you can assume that the line is a linear, it's a linear graph. Okay, so if linear is very easy, you can imagine the y equal to mx plus c. Okay, so what is the stall torque? So stall torque is when the motor is running, then suddenly you stop it from running. Okay, so from you stop it, stop the motor from running. Okay, so the motor will stop, however the supply is still ongoing, so you can feel some strength over there. Okay, so that is what we call a stall torque. Okay, when the motor is not moving. Okay, so the when no load, what is no load speed? So it means that the motor is running freely. Okay, okay, what is the rate here? So actually the rate things here is actually the power. Okay, so which means that the power is equal to torque times by rotational speed. In the same meaning is the area below the graph. I can say it's a area of the graph over here. Okay, so same goes here. So when it at the in the middle of the graph, so you can see the area of the red area here is bigger. So it means that when the area is bigger, it means that the power is the highest. So at this point, at the middle, okay, 0.5 of the torque and also 0.5, not 0. I mean the half of the graph, in the middle of the graph. So the max power happens. Okay, so you can draw the area. Okay, you can see the area. So the smaller the area, mean the lower the power. So you can go to this link for more detail about these explanations. Okay, this is a very good link. So you can go here and you can study detail about the motor, the torques. Okay, okay, I hope that you can study more here. You can gain knowledge in here. So you can see here the power is torque times by the rotational speed or the angular velocity. Okay, so this is the basic graph. Okay, so the explanation about the stall torque, no load torque. So this is the linear graph. Okay, the linear, when you do the linear for using the mathematical equation, so you can get the motor equation here, the torque motor and also the angular velocity as equation. Okay, so this is the speed of the Maxent motor. Okay, you can see it's a linear. I can say it's a linear graph. Okay, same goes to this slide. Okay, so this is the explanation about the in detail about it. Okay. Okay, now we go to the magnetic force and torque. So I believe you see or you saw this slides before. I make some changes here. Just here, I change the torque and the I change here. I use the capital I. So previously I use a small letter. Still it's the same. Okay. So this equation is where this equation come from. Actually from the torque, basic torque, and also the magnetic field, the length, and also the radius, the number of turns. I believe I explained before about this slide. So please remember about this equation. Okay, what is the voltage regulation or the VR? Actually, it's the ability to maintain a fixed voltage under the different load condition. Okay, the VR calculation requires that you know the voltage of your battery or voltage regulator under a full load. Okay, for example, a laptop. Okay, you have a power supply. You on the power supply and then you on the laptop. Okay, which means that your laptop is running. Then you measure the voltage. Okay, that means that it's a full load condition. Okay, and then the calculation also require that you know the voltage of your battery or voltage regulator under a no load condition. In easy or simple condition where that you supply a voltage supply, you supply a voltage to the laptop. However, your laptop is in off condition. Okay, so you know, then you measure the power supply. So what is the power supply during the laptop is off, and also the power supply voltage during the power supply is running. Okay, so this is the equation. So of course the no load voltage is higher than the full load condition. In the other way is they call it as a V rated, or I can say it's a design condition. Okay, for example, you design a laptop that can run at a certain condition, so means that that is the full load condition. Okay, so this is the equation. Okay, for more detail please go to this link. Okay, and then the efficiency of the DC machine. So actually is a ratio of the useful output and the input. Okay, so for efficiency the perfect value is 100. Okay, the perfect value is 100. So for this the perfect value is 0. Okay, the perfect value for this is 0, which means that the lower the regulator the voltage, the lower the voltage regulation means that the better for the system. Okay, for example, the power supply is 12 volt and then V rated also 12 volt. It means that the device can maintain the fixed voltage. Okay, can maintain the fixed voltage. Okay, so for this case also the same. So the output and input must be the same so that you can get the 100%. So this 100% is better, and this one is 0. 12 minus 12 becomes 0, and then of course the percentage becomes 0. Okay, so for this is 0 is better, and then this one is 100 is better. Okay, the efficiency actually is the output divided by the input and times by 100, or the output divided by output plus losses. Okay, how many loss? So maybe the frictions, the temperature, the heat, and so on. Okay, in other words, we can also change the input, the efficiency, which is the input minus losses divided by input. Okay, and then times by 100. Okay, so what kind of input we want to measure here? Okay, so actually we want to measure the power. Okay, the power output and also the power input. So we the power output is similar to the power in minus power loss divided the power in. Okay, so this is the characteristic that we can summary for this chapters for the part 1. Okay, so the torque. Okay, what is the armature constant, the flux, and armature current. So we can see here the torque actually is perpendicular to the machine construction, flux, and also armature current. Okay, so this is the voltage regulation we explained before. where the NL is the no load, and the speed regulation. Okay, speed regulation also the same, where we want to maintain the speed. Okay, at the speed. So with no load, what is the speed? And with the full condition or some condition, we call it as a N rated. What is the condition? Okay, so the calculation become the we can say is a regulation. Same goes to the efficiency of the machine. Okay, for example 1, so we have here a 100 kilowatt and a 1800 RPM generator, so operating at the rated load has a terminal voltage of 240 volt. 240 volt. Okay, so this is the rated voltage. Okay, so if the voltage regulation is 2.3%, so determine the no load voltage. So what is the equation for this? Okay, we can use the voltage regulation equation, so which is this equation. Okay, so we have the value of voltage regulation, which is 2.3. no load we want to find, and the V rated is 240. Okay, so we include everything what we have in the equation. Okay, and then we try to simplify the equation, and we can get the value of 245.5 volt. So you can, if you can see here, the voltage no load is higher than the V rated. Okay, so the regulation is 2.3. okay, it's very less. I can say it's a very less. So for this kind of example, I want all of you to do it and send to me to the author. Okay, and then I will count it as a attendance. Okay, and okay, that's all for this part. So we will continue to the next part.